In today's AP Chem review, we're going to look at a calorimetry problem where we mix two compounds together and then have to determine the heat and enthalpy of reaction. I do like to set up diagrams when I'm doing these questions. It just helps me visualize what I'm looking at. And calorimetry problems, they can become a little bit complicated because there are so many steps. Okay, so let's draw a diagram to visualize the question. We're mixing 100 milliliters of lactic acid into a calorimeter. So lactic acid is C3H6O3. And we're mixing 100.0 ml into a calorimeter with 100 milliliters of sodium hydroxide, okay, so with the same volume of NaOH. Now notice that there is concentrations given to me as well. I don't need that right now, but I'm going to keep that in the back of my mind. We'll come back to that data. When I mix these compounds together, I'm going to have a total volume of 100 plus 100. So in my calorimeter now, I've got 200.0 ml of solution. So what does that represent? That actually represents the surrounding, because if you think about it, we've created water and then an aqueous salt. So water in calorimeter problems represents the surrounding. So remember that these terms are important, understanding what is the system and what is the surrounding, and then in which way does heat transfer between these two components. The surroundings just represents everything outside of the reaction, and that does include water. So because we've created water and this is a surrounding, I can also say that this has a mass value of 200.0 grams, because we know that 1 gram of water equals 1 milliliter of water. Okay, so that is important because it will help me do this first question to calculate the heat. So let's call that part A. Heat has the variable Q. Now, to be again more specific, I'll call this Q of surrounding, Q that represents the water, heat transfer into the water. And the formula for this is the M, so mass, times specific heat capacity, times delta T, which is your temperature change. Now, we just determined what the mass was because we looked at it on our diagram, and the other two variables are given to me in the question. So now we can plug these in and go ahead and solve Q of surrounding. So the mass here again is 200.0 grams, and yes, we do need to write the units down. The specific heat capacity is here. It's 4.2 joules per gram degree Celsius. And then the temperature change, it's final minus initial. Final temperature of the solution is 23.2 degrees Celsius minus the initial temperature, which was 20.0 degrees Celsius, okay? So we put the units in to show that grams cancels out with grams, degrees Celsius cancels out with degrees Celsius, and I'll get an answer here it'll be positive. It'll be positive 2,688 joules. Now I will round this to correct significant figures. We do need to round it to the lowest significant figures. Now this constant, or this value here, it is a constant, it's not measured. So I'm going to look at the smallest significant figures, that's a measured value, and that's the temperature. There's 3 digits here. That number comes from a thermometer. So I'm going to try to round my Q of surrounding also to 3 significant digits. So this would be, we're going to have to do this in scientific notation. This will become 2.69 times 10 to the power of 3 joules. That's how we do part A. Okay, and if we go back to our diagram to visualize what's going on, when you mix these compounds together and these react, 2,688 joules of energy is being released from the reaction into the water. The water is getting hotter. That's what your Q, sir, your positive value represents. And this, by the way, also represents an exothermic reaction. Okay, how about part B, enthalpy? Okay, enthalpy, first of all, let's write down the formula. That is delta H of the reaction. That equals Q of the reaction divided by moles of your limiting reactant. So what I have to do now is I have to figure out, well, what are these variables? What are the values? That's not shown to me directly in the question. Let's start with Q of the reaction because that's an easier one. Q of reaction is always equal to negative Q of the surroundings. Okay, now think about that logically, because what this means is if the water gained 2688 joules of energy, that means the system or the reaction lost 2688 joules of energy. So that means that that's the law of conservation by the way of energy, right? Energy is just being transferred from one area to another, in this case from the system to the surrounding. So Q of the reaction here is negative of the value, but we have to be careful because, again, here's another small point in calorimetry. Delta H is expressed in kilojoules per mole, So we're going to change the joules to kilojoules, okay? So 2688, the decimal is here. 1, 2, 3, move it 3 to the left. This becomes negative 2.688 kilojoules. And again, if we want to do it to the, I guess we can leave an extra decimal here because that's not our final answer. So I'll just leave it like that. You can refer to the AP answer key to see like proper rounding rules. I'm just going to leave an extra digit because that's not my final answer yet. Okay, so I have Q of reaction. How about the mole? Well, the mole of what? So the mole of the limiting reactant. And we're lucky that in this question, both of these reactants are limiting. I have the same volume and same concentration of lactic acid as I do the sodium hydroxide, 100 milliliters and 0.500 moles per liter. So both of them are limiting. It doesn't matter which one we choose. Let me maybe write it over here. I'm running out of space. So the moles, let's just pick the sodium hydroxide. Again, they're both limiting because this is a 1-to-1 mole ratio and I have the same amount of both. So the moles equals concentration times volume. Again, a lot of formulas, a lot of little steps and calculations to be aware of. Okay, moles of sodium hydroxide, my limiting reactant, 0.500 mole per liter, divided by, again, the volume. Again, we have to be careful. You can't put 100 milliliters. We need to change it to liters, so 0.1000 liters, so that liters will cancel out, and that will give me a mole value of 0.05 mole. Okay, great. Now that we have all that information, let's plug it into our delta H formula. I won't rewrite the formula because it's at the top. Delta H reaction equals Q of reaction, negative 2.688 kilojoules divided by 0.05 mole. And I'll get a delta H of reaction here of negative, and again, I'll round it to 3 significant figures to represent the lowest measured value in my question, which is the temperature. This is all part of the same question. So the answer here is negative 53.8. And put the units in your answer, kilojoules per mole. Again, it's exothermic. The reaction lost energy, the negative sign shows that. The water gained energy. Okay, so that relationship shows me that it is an exothermic reaction. So a little bit of a complicated problem, a lot of steps and a lot of units and formulas to use, but I hope this helps you clarify a little bit more of calorimetry. There are different types of calorimetry problems as well to be aware of, such as dissolving salts. So take a look at those different types of problems for your review. Best of luck studying, and thank you so much for tuning in. Bye.